Let's do this problem now. Calculate the integral of f(x,y,z) equals x. So our integrand is going to be simple. It's going to be x over the region given by, and now we are given three inequalities. Okay, so these three inequalities will determine the region of integration. So the inequalities are x bigger than 0, bigger or equal, y bigger than or equal to 0, and then z is between two numbers, between x squared plus y squared, but below 1. Okay, so very important, you need to have sufficient intuition and mastery of functions to be able to imagine this in your head. Okay, and it would be a very typical problem to first sketch this region of integration. So let's do it. This is what the region of integration looks like. Okay, so we are in 3 dimensions, x, y, and z. So first, x is positive, which means that we can forget about anything that is to the right of this plane. So we can forget about all of that. Everything will be to the left of that plane. Then y is positive, so we can draw a plane y equals 0. So all of our region will be to the right of this plane, which means that we will always be in the positive quadrant of x and y. Okay, so those are easy. The slightly trickier one is this inequality here. So it's telling us that z has a lower limit of x squared plus y squared and an upper limit of 1. The upper limit of 1 is very easy. It's just a plane at z equals 1. So this is just a flat thing. The lower limit is x squared plus y squared. So what does x squared plus y squared look like? It's a parabola. It's a parabola that is symmetric around the z-axis. Okay? So it's this parabola here. Right? So, as I said here, this surface is z equals x squared plus y squared. Now, later, we might need the equations for this line defined in the yz plane. So this is the yz plane. So this line is a function in the yz plane. And we might need it later. So how do you find it? It's very easy. You have the equation for the surface. You substitute x equals 0. So this goes away. And you end up with z equals y squared. Okay, so in this plane, this is just a parabola, z equals y squared. Now, what about the plane when y equals 0, this plane? What is the equation of this parabola here? When does this surface cut the plane y equals 0? So you substitute y equals 0, and you get z equals x squared. So that is the equation of this line here. Okay? Finally, we might also need the equation of the projection of this whole volume into the xy axis. So when you project this into the xy axis, you get this quarter of a circle. Yeah, so this is a quarter of a circle. And what is the radius of this circle? You need to be able to figure these kind of things out. So the radius of this circle will happen when the function x squared plus y squared touches the plane z equals 1. So you can equate x squared plus y squared equals 1. So at this point in the upper edge, so at this edge here, you know that x squared plus y squared will touch the plane equals 1. But this is the equation of a circle with radius 1, right? So that is exactly the equation of this circle here. X squared plus y squared equals 1. Okay? So always really important to be able to picture this thing, either do a sketch or draw cross sections. Okay, maybe we can draw a cross section in the yz plane. Let me do that. So sometimes it's useful to draw cross sections. So let's say that this is y and this is z. How does the cross section look like? So we are focused on this plane here, which is the plane x equals 0. So we know that it's limited by z equals 1 on the top. Oops, I want to actually write z equals 1 on the top. And on the bottom is going to be limited by this parabola, which we already know will be equal to z equals y squared. Okay, so this would be the projection of this volume onto the yz plane. Okay? Excellent. So now let's do the integral. We can choose different orders of integration, and in fact I'm going to give you 3 examples. I'm not going to solve the 3 of them, but at least I'm going to write down the limits for each case. Okay? So first let's consider that we start by integrating along z, then integrating along y, and then integrating along x. Okay? So let's write the limits of this first integral. Fine. So first let me write the 3 integrations. And the function that we are integrating is the function f of x, y, z equals x. So that is going to be the integrand that I write here, x. Okay, so we first integrate along z, then along y, and then along x. So let's figure out the limits of each integration. We need to figure out 6 things. So first, integrating along z. So you picture lines that are at an arbitrary point in the xy plane, but are parallel to z. So we move in the z direction. Okay? So you picture this line. So when does this line enter the region of integration? It enters whenever it intersects with the z equals x squared plus y squared surface. So this will be the lower limit of this integration. Okay? So this will be x squared plus y squared. When does this line exit the region of integration? So this line exits the region of integration at some point here at z equals 1. So that will be the upper limit for the z integral. Okay? So next, we need to figure out the limits on the y integration. So to do that, we have to project the entire volume into the 2 remaining variables, which are x and y. Therefore, we have to project this volume onto the xy plane. And what we end up is with this area here. Okay? So we end up with that area. Let me actually highlight it. So now we are integrating along y. So what I do is I draw a line in the y direction. And then I think, okay, when does this enter the region of integration and when does it exit? So it enters the region of integration when y equals 0. And it exits the region of integration when y is what? I need to solve this equation for y. So I need to solve for y. So y equals the square root of 1 minus x squared, right? I have solved for y in the equation for this circle. So that will be the upper limit, square root of 1 minus x squared. Okay? So now we have integrated along z and then along y. So we project this area onto the x-axis, which is the only remaining variable. And therefore we have to integrate between 0 and the radius of this circle. And the radius is 1. So between 0 and 1. Okay? So that would be the limits of integration for this first case. Now let me see what happens if I choose first integrating along x, then integrating along z, and then integrating along y. And let me call this I2. So first integrating along x, then integrating along z, and then integrating along y. Okay, so we start with our volume. In the inner integral, we start with our volume. We're integrating along x. So now we draw a line in the x direction. Okay, so what is the x direction? So it's difficult to draw in this diagram, but the x direction is something like this. Yeah, it's parallel to the x-axis. So it enters the region of integration in this region here, which is the plane x equals 0, right? So it enters the plane x equals 0. And when does it exit? It exits when it intercepts with this surface here, which is the surface z equals x squared plus y squared, which we will need to solve in terms of x. So we will need to write everything in terms, so we need to solve for x. So x is going to be the square root of z minus y squared. So that will be the upper limit, square root of z minus y squared. Okay? That will be the upper limit of the inner integral. So now we focus on the second integral along z. So to do that, we get our volume and we project it into the two remaining variables, which are z and y. So we have to project this into the zy plane. Fortunately, I already had this drawing here. So this is the projection of this volume into the zy plane. So now we are integrating this first along z. Okay, so if we are integrating along z, I imagine a line in the z direction. So we enter the region when z equals y squared. And we exit the region when z equals 1. So the upper limit is 1. Oops. Sorry for that interruption. At least I made that time useful and I tried to make this a bit neater because everything was very squashed, so now I have more space. So where were we? We had found the integration along z, which was this line here. So we enter at z equals y squared and we exit at z equals 1. And next we need to project the remaining area on the remaining variable, which is y. So we project this area onto y, and what do we get? We get this interval here. And this interval here goes between y equals 0 and y equals 1, right? Because that's when z equals 1 and z equals y squared. So y equals 1. So between 0 and 1. And that will be the triple integral. And the results should be the same. Finally, let me do one last example. So let's say I want to start with x and then y and then z. Okay, so this is my integral E3. So x, then y, and then z. Okay, so the x integral is the same because we start with x in both cases, so the limits are going to be the same, 0 and square root of z minus y squared. And then we need to project, we are left with y and z, so we need to project the volume into the yz plane, which is again what we had here. But now we are going to integrate along y. So what are the limits? Well, we draw a line moving along y, and we say, when do we enter the integration region? We enter the region at y equals 0. So that's going to be our limit for y, lower limit for y. When do we exit the region? We exit the integration region at this curve z equals y squared. But we need the value of y, right? So we need to write this as a function of y. So y equals the square root of z. That will be the value of y at which we exit the region. Therefore, sorry if you didn't see, y equals square root of z. So that will be the upper limit in y. And finally, we project this area into the remaining variable, which is z. So we project it into the z-axis. So we need to integrate between z equals 0 and z equals 1. So that will be the outer limit between 0 and 1. Okay, so those are three different ways of calculating the same integral. And the three must give the same result. So let me do one of them, okay? I'm going to choose the third option. Even though it has square roots in the limits, which could be scary, you can see that when you integrate x, you will get x squared. So when you substitute the square root will disappear, okay? And then you will have a z minus y squared, which when you integrate with y, you will have probably nice things. So let's try to do it, okay? So let's try to do this third method. So I3 is, so I'm going to leave, well, why not? Let me copy this, squish it a little bit. So I leave the outer integral. I also leave the intermediate integral. And I want to solve the inner integral. So what is the integral of x dx? So it's given by x squared divided by 2. But we have to evaluate it between 0 and the square root of z minus y squared. And then we later have to do dy and dz. Okay? So if we do that, we end up with the integral between 0 and 1 of the integral between 0 and square root of z of z minus y squared. Because the square root cancels out with the square, right? Divided by 2, so with a 1/2 in front. dy dz. So now we need to integrate this with respect to y. Okay? And the integral of that with respect to y, so we leave the outer integral unchanged. The integral of that with respect to y is going to be 1/2 zy minus 1/6 y cubed. Yes. And the limits are between y equals 0 and y equals square root of z. Okay? And then we still have dz. So now I have to substitute y equals square root of z and then subtract when y equals 0. So what I get is the integral between 0 and 1 of 1/2 z times square root of z, that is z to the 3/2, minus 1/6 times square root of z to the power 3, that is 1/6 of z to the power 3/2. Okay, and this we need to integrate with respect to z, but actually 1/2 minus 1/6, that is 1/3, which we can keep outside. So this will be 1/3 of the integral between 0 and 1 of z to the 3/2 dz. And what is the integration of z to the power 3/2? That is simply z to the power 3/2 plus 2, which is 5/2. But then if we do the derivative of this, we would get 5/2 in front. So we compensate by adding a 2/5 in front. And this evaluated between 0 and 1. And the final result is therefore 1/3 times 2/5 minus 0. And this is equal to 2/15. And that is the correct final answer. Okay? So there you go. A triple integral in a really nice region. Okay? So we could have calculated the mass of this object when the density of the object is equal to x. So this object weighs more in this corner and it weighs 0 in this plane of x equals 0. So the weight is increasing in the x direction. That's why the density would be equal to x. And we have integrated that function. So we have integrated f of x, y, z on the whole volume. So this could be interpreted as the mass of this object if this is interpreted as the density, for example. Yeah. Okay, good. See you in the next video.